Okay. Good evening. So today what I'll do is last day we stopped at the forward propagation of a neural network. Today, what I'll do is I'll also start with how to train this neural networks is what I will try to see. So recall from the previous class. So if you have a layer in a multi-layer perceptron, the output of the jth neuron is given by all the inputs from the previous layer. So you have ZL minus 1, 1 dot 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 all the way to ZL minus 1, NL minus 1. So you had NL minus 1 neurons in the previous layer, and you're going to take the linear combinations of all those and get one output from that neuron. That's the output of a neuron. Then you pass it through some function, some activation function to bring in nonlinearity f. And what you'll get is you will get the output of that layer. So for every neuron in this layer, you will do the same thing. And then you can just vectorize this in this format, right? So you can take this is since it is a vector sum of wji zji. So you can simply write this as a vector matrix product wz plus b. So the idea is, so here the wz will transform our L minus 1 dimensional feature to a L dimensional feature. So this is nothing but a linear transformation using all the features in the previous layer. Then what you do is you pass it through an activation function f. And once you pass it through this activation function f, you get the output of this layer. So this was the recap of what we had done in the previous day. And now onwards, I'll be talking about how to train this model. Is the topic of our discussion over the next 10, 15, 20 minutes. So what we'll try to do is recall that the objective that you have, Wji, are weights, right? So they are weights of every layer for every layer L for all L, I, and J. So for all layers, we would need to do gradient descent, right? We would need to assign them back to, this is the steps that I need to do for all the weights. Similarly, for Bj of L, I need to do Bj, the bias term of L minus eta times dl db j of L. And I will keep on doing it until convergence. This was the gradient descent algorithm. But you see, there's a problem with the gradient descent algorithm over here directly. This is because each function that you have is a linear, direct derivatives are tough to compute. Because for every wi, you will have to take, since there's a composition of functions, right? So they are one layer depends on the other and so on. So your output at zj L is a function of L f1 or fl fl minus 1 dot 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 f0 of the features. So you have very, very complex functions that you have. So if you just have to take a derivative of the loss with respect to these features, you will have to, or take the loss with respect to this feature x, whatever zj with this features x, you will have this chain rule that you will get f dash and so on. You'll get this continuous chain rule. And since we saw in the last class, this is also going to branch out. This is going to branch out because we saw in the previous class that if you have this is exactly the composition like this. You had this independent variable u and v, and you passed it with functions x, y, and z, and you get the function f. So you get a linear combination of all these derivatives, all the derivatives that branched out. So if they were x that depended on u, y that depended on u, z that depended on u, then if f depended on x, y, and z, so then you would have to see the derivatives of f with respect to x, x with respect to u. We'll have to basically check the change of x, y, and z for every change in u or the input variables. So you see it becomes very complicated just if you do keep on doing these derivatives for every input, right? So if you keep on doing this derivative for every input, it becomes very, very challenging. So the idea is, how can you simplify it? So how to simplify it, there's a simple way. That is what we do in backpropagation. So you see, when you have one layer, I'll just give you one intuition and then I'll start with the base case. So if you have one layer, right? And if you somehow want to calculate dl dw ijl, can I do this way? Can I do this by writing dl dz l plus 1, right? To which I? So this will be to the ith input. So since you are getting this output from this, say this ith input. So whatever weights did you have, say your weights, you're taking the jith weight, you want to take the derivative of, you can simply do that by taking this chain rule, right? So you can start off with dv. So let us start off with this equation. So this two equation. So if I can write dzl dvj of l, then I write dvj of l dw of ji of l, right? So for the jth derivative, I'll get it from these numbers, right? And then you see this is nothing but tau z l and tau w ji l. So now if I somehow know this value tl dzl, I'll be done. This is the idea of backpropagation. So this is also known as the local gradient, and this is what is propagated from the back. Propagated gated from future layer, not next layer. This is how you propagate it from the next layer. That's the idea. So what you see over here is, so dl dw can be written this way. This is what this is the intuition. Sorry. So this is the intuition that I have. That for the sorry, I think I can't see my screen. Okay, now you can see the screen. Yeah. So the idea is, once you'll be able to get these values, this is nothing but dz dw ji, you will be able to use the next layer's output directly, because that's what you'll be transferring to this and simply use that to get the derivative of the wji. So, but the only problem we are seeing is we need to propagate this backwards. So till now, what I have done is I have been doing just revising what did we write in the last class. So if you recall, we wrote the forward propagation as linear combinations of the previous layer's features. So I've written that on the left side here. And then we were telling you that how will we train these neural networks, right? This was the objective. So to train this neural network, we saw that we would need backpropagation, right? So this is the, am I audible? I've been teaching for like 10, revising for 10 minutes now. Can you hear me? Okay. So the idea is you would need to backpropagate the loss for every weight in the neural network. For every layer, every weight that we have seen was changing your features from a previous layer size to a next layer size. So, but how do you do that? I gave the intuition that if you have a series of functions, and we saw last time, it opens up into multiple derivatives direct if you just take chain rule, right? So just taking derivative in the forward state using chain rule can be very, very long and lengthy. So we need to do something that is a bit intelligent and subtle. So to do that, I'm trying to bring to your attention that, let me write it once again so that you follow. Say, how will you get the, say you have an intermediate layer L, right? This is the intermediate layer L I'm dealing with. And I want the, for this intermediate layer, I want the derivative of every weights in that layer. So what are the weights in this layer? The weights are Wji L, right? These are the layers, these are the weights. These weights I need to update. Do you agree? So how do I update this? So you see, we had these two equations here, right? So can you tell me this term dzl dw jil? How do I calculate this? Can you tell me? So I'll just give you, this is the intuition that I'll be using. And then I will show you how will I backpropagate this loss. First, but let us see how can we take the derivative of the output with respect to the weights. Can you help? This is a simple problem. Can you help me do this?
Okay, like using that equation zj equals to fvj. So
Yes.
we can,
So I will tell you to use chain rule once because we'll be using that continuously. Can we write this as ZJL by DVJL, right?
yes, then vj with respect to w.
Good. DWJIL. Good. This is good. I know both of these values, right? Just tell me the both of the values. So first, this value is if L prime VJL. Yes. This is the derivative of the function
Yes.
into what? The derivative of that will be simply WJI of L. Do you agree? Or sorry, Z L minus 1I. Yes or no?
Yes.
Similarly, I will also get dou Z Lj dou B as simply FL dash VJL. Do you agree? Because it's the constant. So both the parameters I got a derivative somehow. So this product is called a local gradient. We'll see why. Local gradient, and in books it is sometimes referred to as delta L because it's a local gradient of layer L because it helps in minimizing the notation, but I'll not use it here. I'll just use it in the code, right? This product of the function into the input that you're getting at I, right? This is the ith input. So be careful. This is the input. So let me write it I i's are the input, right? This is from the previous layer, right? Are you following? The I, Zi, L minus 1 are from the previous layer. Do you agree?
Yes.
And so these are the inputs. And the outputs are ZJL, yes or no? And they are linked by some W. But now you tell me, what is the desire of me? What do I desire at the end of the day? I desire the derivatives of the weights with respect to some loss, right? You want to optimize for that loss, minimize the loss, right? What is the objective at the end of the day? If neural network is f theta, you want to find argmin of theta, right? This is what you need to find at the end of the day.
Yes.
So with respect to what do I need to? So L theta I will write instead of, I need to take the derivative with respect to L, right? At the end of the day. With respect to the loss that I'll be encountering at the end, the task that I'm going to do, with respect to that, I'll be taking the derivative. So can you tell me what should I do to do that? Here and there, you will see the idea of gradient descent. What should I do with this to convert it into?
But Dada, we have not defined the loss like here.
Just think there is some loss at the end. I'll tell that. What do we have to say? Say L is the loss. I will define the loss. For the time being, let's just forget about the loss. Think L is the loss. If I have to convert this into some DL, DWJI, L, what should I do? I will do that step afterwards because that will help you to complete the story. But let us think that you have the
DLL, del, dow L,
good.
dow Z.
Exactly. Dow L, dow Z, J from layer L. Right? Dow L, dow Z, J from layer L. So if I have this value, I will be done. Right? Dow L. I'm going to complete this thing first, and then I'll be going back to the loss. I hope that will work for you, right? Is that okay? Loss, I'll tell you. But for this layer, is it
Okay.
clear? Is the math clear first? We'll write down the formula, then we'll see how we are implementing it. Yes, this is what I'll get. Right?
Yes.
So let me write it down in a fresh way and write the vectorized implementation, and then we'll go to the loss. So dow L, dow WJI of layer L. This is for one data point. We'll see why is it I'm saying that. So you are going to get, what are you going to get? FL VJL dot ZI L minus 1, this into tau L, tau ZL, right? This is what I got. Now, in a vectorized form, what can I write? As in matrix operation. In form of matrix operation, what is the dimension? What should be the dimension of DL, DWL? Since I wrote the vectorized implementation over here, V as some WZ plus V, Z as some F of VL. Just let me know what should be the dimension of this. Dimension of DL, DW. It's a derivative with respect to all of the components, right? So what is the dimension of W? WL of the Lth layer, if you remember. So what does the Lth layer do? It converts NL minus layer, NL minus 1 layer to NLth layer, right? That's what W does. So number of features from NL minus 1 to NL features it will convert, right? Okay, so what is the dimension of W? Yes or no? Can you see this equation? This equation is what I'm using. So NL equations and NL minus 1 unknowns. Okay. So the dimension of DL DW will also be the same that we have seen. These gradients are of the same dimension. Since gradients are of the same dimension, will just be the same product. So you see, this is how much dimension? This is of R to the power of, so Z, just note, ZL minus 1 belongs to R to the power of how much? NL minus 1, right? And Zj of L belongs to R to the power L, right? So these two is what, so we want to make this into a product form. So what will I do? I'll simply write this as FL Vj of L, a Hadamard product, since these are always 1-1 multiplication, right? So did I write this WZI DL? Yeah. So this Hadamard product with DL DJ, because since they are the same dimension. Okay, did you listen to what I was saying? I think you fell out of the call. So the dimension of W is the same as the dimension of the dimension of W is number of equations that W will give into number of unknowns it will get, right? So previous layer will give it NL minus 1 inputs and it will give L outputs, right?
Yes.
So the derivative will also have, the gradient will also have the same dimension. Do you agree? Has to, because gradient is the derivative of the output with respect to all of the features. If you take a vector, right? That's how you define the gradient. It's the stack of all the derivatives. Here I'm going to stack it as a matrix. Doesn't matter really. Any questions? So I have got this value. What all I am trying to do is write it in terms of a matrix product. So I was saying that dz of L is L dimensional, NL dimensional, and dz of L minus 1 is NL minus 1 dimensional. Do you agree? Right? Somehow if I take the dot product of these two, I'll get all these products. Yes or no? That I have written here. This is like AIBJ. When will you get AIBJ? If you take A, B transpose, right? If these are vectors, you'll get. So therefore, I can write this as DL, DZ, J of L into Hadamard product of FL, VL of J, VJ of L. Dot product with Z I or Z L minus 1. Right? Now you see this dimension is NL cross 1 and this dimension is, or transpose will be here. So 1 cross NL minus 1. So you clearly see that this dimension DL, DWL will belong to R of NL cross NL minus 1. We're pretty simple. That we had over here. So if there are even n operations, this one will become n and there will be still no problem at all. Right? If there are n data points, so you can write this directly as a sum of all those data points. This is not going to affect your results anyway, right? So all I did is I wrote this derivative in this vector form. So because aibj means ab transpose, I just wrote aj transpose. And when I write that, it doesn't matter the number of training examples I have, because 1 and n both will give me nl and nl minus 1 into nl minus 1 dimension. That's the idea. Similarly, dl db will be, just see what did I write? F dash l into vj of l into dl d v l or dzl, correct. This is this dz of l, right? No problem. Now if it is, now again this is nl dimensional cross n dimensional. If it is n dimensional, n data points, you sum over all data points, or average expected value over all data points. So n, that is, you can sum over all j equal to 1 to n, 1 by n. But basically, did you find this idea clear? So this vectorized implementation, once if you're not following exactly now, listen to what I said just now, because you fell out of the call, and just try to map it to what I said, because I just wrote whatever I wrote in scalar form into a vector form. That's what I did. But the idea of the derivative with respect to the weights for every layer, I know now, right? If I can somehow define the loss, I'll be done. Do you agree? And you have told me how to calculate it.
Yes.
So for that, I have to define a last layer. So in the last layer, you will be given some labels, right? Say, for example, you want to predict a house price. That example I'll show you today. And you have, say, x1, x2, x8 features. 8 features, say height, perimeter of the house, the square feet, the location, all these are features. You pass it through some neural network. And at the end, you get one layer, one output, right? Do you agree? You will put one neuron to predict the value of the price. Okay, I can just do this by simple matrix multiplication and linear combinations and adding this non-linearities that I defined. I'll get one output. Okay, and I want that output to give me the price, right? So how will I train the model? Any idea? What will I give the loss to the model? Say the actual price. So what is the data set? X, comma Y. X is the features of the house. Say pay area, number of rooms, bedroom, etc., etc. Y is the price, the rupees 1.5 crore, right?
Like minimizing the y.
Good. Minimizing the Z out and Y. In this case, this will be nothing but the square mean square error, Z out minus, just like regression problem, right? If it is classification, we can put the logistic regression loss, right? Whatever we want to, right? I'll do one today. I'll give you as a as an assignment question for a logistic regression problem. Is this okay? Is it clear to me? Clear to you?
Yes.
Okay. So then if there are k outputs, say you want to predict the house price, you want to predict when it will be bought, you want to predict that how much can you get, you want to predict if the house will break down, or if you want to predict some other classification problem where you want to predict cat, dog, there are 100 classes. So for them, you need multiple outputs, right? Do you agree? For example, we showed in softmax regression, we needed k outputs if there were k labels. Do you agree? So for each of the output, there will be some loss. Yes or no? because there will be a corresponding label to that output and you want to train, and there will be other labels. Do you agree? Any questions? So for the last layer, say the last layer is output is ZL, capital L, because we had L layer neural network, I from 1 to K. The K labels, K features, whatever you want to predict, you just give that as output, and then you will have losses, right? For each of these predictions, you will have some loss, and you will sum up the loss because you want to minimize the total loss, right? That's what I wrote.
Yes, yes.
So now, what did we need? We needed DL, DZ, DL, right? DL, DZ, yes or no? If we had DZ, DL, DZ, we could do the next steps in the intermediate layer that I showed. Do you agree?
Yes.
So now see, it's just the base case. It's a recursion problem. Just DL, DZ you will do. You will get this value. This value is known to you. So for MSC, it will be nothing but Z minus Y. Yes or no? For MSC. Clear? Can I continue? But am I done with the algorithm? If you're following me, I have not completed one step. And this is where I'll use the chain rule that we did last day, the entire multivariate chain rule. Can you tell me what step I haven't done? DL, DZ, capital L for the last layer I calculated. And I calculated, given that DL, DZ of the future layers, I calculated the DL, DWs for the past layer. But what haven't I done till now? Can you tell me?
For the first layer.
For the other layers, good. Not first layer, or any intermediate layer, I have not calculated the. So if you have a feature, if you have a Zi, right? Z L minus 1. So till layer L, I have calculated, say small l, Lth layer. This is how you do recursion. Till Lth layer, I know, but I do not know L minus 1 layer. Do you agree? I do not know the derivative of. So I was given the derivative of DL, DZ. Yes or no? This one I was given. But what do I have to give back to continue the recursion? What do I have to give back?
Oh, like previous one, I will give back
Good.
to reach the
You
first
you
one.
have you not first one. It's an intermediate. So at the end of the day, when L will go to 0, you will reach the first layer, right?
That is only I am telling. To
So you have to give this, right? You have to give the gradient of the input with respect to the L minus 1th layer, correct? That I have to pass back to the previous layer so that it can calculate the derivative with respect to the W's weights. So this is the recursion step. Okay. Is it clear? Can I go to how to do this? Go do this. Okay. So you tell me, do you remember that all these neurons dependent on the output of Zi? Do you remember that in the next layer? And you had 1J, 1I, 2I, dot, 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 JI, NLI. Right? So you had all these layers, weights to give you the output. So recall, what did you have? You had Z V J of L was summation of J equal to 1 to N L minus 1 Wji L Z L minus 1 I right plus B L. So you sum over all the previous for an output. But since this gave inputs to all these previous next layers, right? Can you hear me? So do you recall that this single neuron gave output to all the neurons in the next layer?
yes, yes.
So is it not exactly the same as this problem that we did last time? These neurons gave output to all of these X, Y, Zs in the next layer, right? The U gave output to X, Y, Z. So what did we see? We saw that when you're taking a derivative, we have to take the changes of each of these X, Ys, and Zs. Do you agree? So presently, I know something. I know this value. I know, and I know ZZ of L is equal to FL of. These are the forward propagation step. Do you agree that DL DZ I of the L minus 1th layer, it is going to be, can you tell me what will it be? It has to be a sum, right? Of all the next layer's weights, as we saw in the chain rule formula. It has to be tau L, tau Z, J of the Lth layer and tau Z L of the Lth layer with respect to tau Z I of the L minus 1th layer. Yes or no? Because the L minus 1th layer, this gave inputs to all of these J's, J equal to 1 to L, NL. Do you agree? So if you understand this, then what can I tell you? What can you tell me rather? You can tell me just put these values. So this I already know from the next layer. I'll just put the value of, just put this value NL. What is this value? Tau Z, tau Z W. So I can write this as, what can I write this as? I can write this as tau Z J L with respect to Vj of L into Vj of L into tau Z I of L minus 1. So what is this going to be? This is going to be I equal to 1 to NL tau L tau Z I of L into what? This value is, this is again we have calculated in the previous example, into, what do you have? You have W. So if you take the derivative with respect to Zi of Vj, you have W Ji of layer L. Excellently put. So you see, again, you have the same formulation that we defined in the previous example, right? So you have these two products, right? Again, this Hadamard product, Vj of L, Hadamard product with DL dz of L. So this is how many dimensional? This is NL cross N dimensional. And this you are going to take an addition over all the i's in the layer L. So that will give me W transpose. So this I'm just vectorizing NL minus 1 cross NL. This is the idea. And this will give me a derivative of tau L, tau Z, L minus 1, which had to be NL minus 1 cross N. Right? So I'm sorry, I defined the local gradient in a bit of a wrong way. The local gradient is not defined over i's and j's. The local gradient is defined over both the j's. These two. So this is defined as the local gradient of the local gradient is defined as tau L tau Zj L. So both the layers L, which is where you have a scalar multiplication, is where you what you define as the local gradient. So this is just for your understanding. So this exactly is your tau L of J, right? So this is where you give the input to the previous layer. So you see, we have been able to complete the loop that we set out for. So we used the chain rule in the previous class, and we wrote it as a sum of the. So basically what is happening, wherever these inputs go to the next layer, you will have signals from those to change your weights. So all this will give you signals. So your back propagation can be simply written as backprop for layer L. You can write this as dl dw for layer L as fl prime vl Hadamard product with tau L tau ZL, and this is your NL cross n dimensional into tau L tau. We did it just now. ZL minus 1. So this was ZL minus 1. This is n cross NL minus 1. So you see this also becomes NL cross NL minus 1 the way that we wanted to define it. So DL dB will be sum over training examples just this value, right? Because Z is equal to 1 in that case, right? You'll have one transpose. So this will give you just the summation of all those values. So if L, this value into DL DZL. And this is NL cross N. And when you sum over all the training examples, you get NL cross 1. This is NL cross NL minus 1. And what you do the recursion as? The recursion, you complete the recursion as tau L, tau Z, L minus 1 as WL minus 1, W transpose. Same thing. This is the local gradient. So if you write it in terms of the local gradient, you can simply write this as delta N. So this is delta L, the local gradient, sum of the local gradient, and delta L is defined as Pj Hadamard product with DL DZL. Please go back, see this again and again. I derived it and see my video. That will be good enough for you to understand all the backpropagation steps, because I have formalized each and every step and have not written anything from thin air. Please go back and have a look at it. So this is how you will train a neural network. But now, once you have trained this neural network, how do you regularize it? We have seen in L2 regularization and so on. There are few ways to regularize neural networks. We'll see just now what is overfitting and so on, but neural networks are very, very complex functions, right? So if you have something like this, your model can just predict each of these fully. Just to regularize it, you can add this penalty to the loss of the W plus the L2 norm. This is also called the Frobenius norm. You add this norm to the W, and then you continue your derivative. This is your loss L2 regularized. And this will be added for all the layers. If you're asking me what is this, Dada, how are you calculating this? So you see this W is what I'm defining as summation of WLs squared, L equal to 1 to L. So for all the layers, I will be just taking the sum of the square of all the weights. So it's basically sum of square of all the weights into some lambda, depending on what weightage you want to regularize. There is also another way to regularize neural networks or MLPs, which is called dropout. So since this model is overfitting too much, you don't want all the neurons in the neural network. You want some redundancy in all the neural networks, all the neurons. So, to prevent or to force the model to use lesser neurons than available, try to make some of them similar. So once you try to make some of them similar, you will solve this problem of make diverse, very, very complex functions being modeled. So basically, if you have 100 neurons, you can make them look like 20 neurons. So how can you do that? You can say with 0.8 probability. So if you want to make it look as 60 neurons, so with 0.4 probability, you set the output of a neuron to 0, right? So you say if the output of a neuron is ZL I, you multiply it with an indicator random variable, right? Where I is distributed as Bernoulli P, right? So this Bernoulli P, if this is 1, then for 60% of the time, this will give you some output. 40% of the times, it will not give you output. So this making it 0 forces the model to retain similar information across this, making them randomly 0 forces model to have similar information across neurons. Okay. So finally, so that was these are the two methods in which you can regularize. But just for training purposes, just remember a rule of thumb. Rule of thumb for training neural networks. So these are the rules of thumb that you need to remember while you're training a neural network. So what are the rules? Number one rule is normalize the weights. Normalize the, not weights, inputs. So how can you normalize the inputs? Say you can divide by maximum value of features. So between 0 and 1, you scale them so in what happens is normally in computers, you will have precision error. Therefore, if you have larger values, they will just blow up and you will get floating point errors. You can also use a x minus mu by sigma as a norm. So this is called Z scoring because you are doing a normal or Gaussian normalization. So you're making this normal 0-1 distribution from normal mu sigma distribution. And how is mu sigma calculated? Mu is the sample mean of the feature. Sigma is the sample variance of the features. This is one. With respect to the inputs, please normalize the inputs. Second, the weights must be randomly initialized. If not randomly initialized, all neurons would end up, if not, all neurons will end up learning the same function. Why? You see, because the updates depend on the, where is it? Yes, this is the backpropagation algorithm. The update depends on the future layers. So if you set all of them to the same value, so dl dz of L for all these features, where did I write? The derivative of this will still be the same, because if the output, there's only one output, say MSE, the derivative for each of the functions will be same. And in that case, your derivative will be the same and you started off from the same W. So what will happen is, so if you just see this equation, I'll just copy it for you so that you understand. Where did I write it? Okay. This is here only I'll write, please initialize weights W0, WT equal to 0 randomly. So you can sample from normal 0-1 distribution, generally what is used to sample. Or you can use something called as a Xavier initialization, which is not in the scope of the syllabus, but you can have a look at it. So you can use all of these features to randomly initialize the weights, because you see, if your loss of y comma z output, ZL, is fixed, your DL DW is DL DZL into FL. I'm doing it for the last layer. And this is nothing but directly with respect to the loss, you'll get it into Z L minus 1 transpose. So if all the weights were same, so then this output would be same. So would be these. This is also dependent on output, and this would be dependent on the loss. If you have only one loss, this is going to give you, so whatever loss you're going to have, this is going to give you the exact value. So this is going to give you a fixed value. So this entire DLDW will be same for all neurons. So when this becomes same for all neurons, so then it becomes a problem. Therefore, you do not learn any new functions. You end up learning the same function. Therefore, please randomly initialize your weights. So with that, we come to end of algorithms with respect to supervised learning. So today, what is the plan? The plan is to understand, since I was telling overfitting and all in neural networks, what is overfitting? What is a bias variance trade-off? And we'll start off briefly with unsupervised learning, mainly clustering algorithms like k-means and k-medoids. Okay, so first we'll try to talk about bias variance trade-off that I have been doing all this while. So I have been training models all this while, and these models are nothing but fit to functions, right? So they can either classify, or they can give me a decision boundary, or it can give me the predictions for a regression problem. So in bias variance trade-off, what happens is, say, consider this picture over here. So in this picture, this blue curve, do you see this is a bit absurd? Do you observe that it is a bit absurd here? But this looks simple and concise. By what do I mean by simple and concise? These are all like qualitative terms. Quantitatively, we will be seeing. So this is trying to see what is called as a Occam's razor. Occam's razor. Some 5,000 years back, Occam said the simplest explanation to a problem must be considered before more complex ones, right? You must not go for first complicated solutions. First, try to consider the simplest one. So in this case, you see it in trying the pursuit to have, so these points that you have over here, they have been cosmetically made to show you noise. So there is some noise in the data, right? So say your data is f of x. So this is a deterministic function plus some epsilon noise 0 sigma square. So you will definitely fall out of the decision boundary that we are seeing over here. So to capture that noise, you are fitting one function that is exactly mapping one function. So then what do you say? You say that this is a very overfitting model. So this is called a overfit. So but this model which you see over here, this model if you say if you have, and then this is an ideal fit because this takes the Occam's razor and valid and works most of the times. But why is it that you are considered? Why not just use an overfitted model? This is because most of the times when you have these models, what will happen? You will have more actual probability having green points here, green points. But in the training set, due to sampling problems, you just sampled some red points over there. So what will happen due to the bad decision boundary that you'll be creating, you will be, see, this will result in prediction, poor predictions on unseen data, which is not in the training set, on the test set. When you take the test set, you do not know what is going to happen, and you see that you will have a poorer performance for that. Okay, if you have any questions, feel free to interrupt me. Okay, so this is the test set that you will be having. From the test set, you will be having a poor accuracy. So so we understood what is an overfit. When overfit, you're trying to accommodate every data point. What is a ideal fit? Let us also understand what is a underfit. So say you have two classes like this. Two classes. So here your ideal decision boundary should be a circle, right? So you should have a circle here, a circle like this that separates these two classes. So if you're able to separate these two classes, you are pretty happy that you are, yes, I've separated these two classes, but this is a more complex decision boundary. Now I tell you, I want a simple decision boundary. So you say you give me this decision boundary. This will not give me any good accuracies. So this is a simple model, but again, a bad fit. So intuitively speaking, if you have a model complexity on the x-axis and you have performance or error, so error is inversely proportional to the performance. So you should have something like this as the curve. So model performance, model curve complexity, you will see that there is an optimal model complexity for a problem. So for predicting images versus a chat GPT algorithm, every one of them have a different complexity level that they need to find. So this is the ideal complexity. Anything above this for the model is known as overfit. Anything below this is known as an underfit. And for the next 30-40 minutes, we'll be trying to understand what is an overfit versus what is an underfit. Okay, good. So, but how do you understand which model is better? You do that by seeing it on a test set. So you will, as I told you, so your training set can be here, but you may sample circles more often here than any red points on the test set. So in the test set, the model has not seen those test points. For example, you have trained the entire image on the on the internet to predict cats, dogs, and so on. But when you take a photo from your camera and give it to the model must be able to say it is a cat. If the model performance decreases significantly on your camera performance, then you can say that the model is overfitting. But there are some other problems as well, but we'll, for the time being, let's say they are. So they have to be. So you say that the model is overfitting to that training set that you have given to the model. And it's not generalizing. The idea is to generalize these models in real life so that you can use them. Otherwise, it's if you just fit the functions, it's just function fitting. So that's the idea. And just to note, the second assignment will be out today or by tomorrow. Third assignment on supervised learning. I have given it is a 30 marks assignment. Please solve it. It has linear problems, SVMs, and so on. And feel free to submit them for correction. And I'll be extending all the deadlines till the end of May, mid of June, so that once we finish the course in next 2 weeks, you can still submit, and then I can correct and you can get the marks that you need. We'll get. So if you're following, please submit the assignment. So before we try to understand if the model is actually an overfit, is an overkill for your problem, or is the model a bad estimate, or is it a poor thing to use because it is not going to generalize because it is going to underfit the model like this, then we need to define some terminologies. The first terminology that we define is the hypothesis space, H. The hypothesis space is what you choose, is a class of functions that you choose or the algorithm that you choose. For example, two-layer neural networks, a linear regression model, then a neural network, then you can have decision trees. All these are the hypothesis space. So you may have, so all W transpose X, this is nothing but W space. So all this W, you're going to pick a specific W, right? This W star you will pick. So this is your hypothesis space, and you pick the optimal. And how you select the optimal, it defines the next two properties, which is bias and variance. So bias is when you have an hypothesis space and you bias yourself to selecting only a few of the W's, then you have your model is said to have high bias. But versus when you give the model free will to select anything in the data set, then it is called a low bias model. Right? We'll see how do we do that. So recall, what was the ridge regression decision problem? Ridge regression loss. Ridge regression loss was equal to yi minus w transpose xi whole square, I equal to 1 to n training examples, plus summation of wi square, I equal to 1 to d features. So can you tell me that what is the hypothesis space here? The hypothesis space is W transpose X. The W comprises of the hypothesis space, all the d-dimensional vectors or d plus 1 dimensional vector, right? Where 1 is the bias term just fitting. Okay, but now if you want to put a high bias into your model, what you can do is put a lambda value greater than 0. So what does it do? It forces you to select lower values of W. Right? It forces you to select lower values of W. So this has not come up on the screen yet. Yeah, it forces you to select. We write it clearly to select lower values of W. So now automatically you're restricting your space to 0, say 0, C or minus C, C to the power D. Instead of R to the power D, you restricted your space between some minus C, C. We'll try to see it mathematically as well, but bear with me with this understanding that a high bias system means you are going for a simpler model. So you can say that these models are high bias, versus these are called low bias models. But remember, bias depends on a different objective. So model complexity here says this over the same hypothesis space. Then, so remember, you must remember the bias is defined for what? A specific hypothesis set. And what is a hypothesis? Hypothesis is the class of functions that you're using to model the data, right? In reality, hypothesis means how do you model the data? You tell that this might be happening because of the results from what you see in the data. That's the hypothesis. For example, if you see what ice melts, you may initially, when it was not a theorem, you may have proved, you may have given the hypothesis since it is hot outside. Since it is hot outside, this heat is being transferred from the to the ice, and therefore it's melting. So this is one example to try to explain a data, and that class of functions that you use to explain the data is called a hypothesis. Okay, so that is your bias. On the other hand, what is variance? So variance is defined as how much noise in the data can you capture. Noise in the data. Data can you capture for a model? So again, for a particular set of hypotheses, see, whenever you have this is where you will get a high variance, right? We saw overfitting. Wherever overfitting happens, how much noise in the data can you capture? So how much can you overfit? So see, in the previous example, you were able to this model, overfitting model that we defined, was seen to have a very, very high variance because it was able to capture the variance in the data, the noise in the data. Correct? This is also known as the high variance point. This is high bias or low variance point. Clear? Any questions? Okay. So when you have wherever you clearly, if you restrict your systems, you will have restrict your systems. You will have high bias, right? And low variance. So if bias increases, your variance will generally decrease. This is called the bias variance trade-off. We'll try to see it mathematically now, but intuitively, this is the idea. So when you are making models simpler models have high bias compared to and low variance. Similarly, complex models will have low bias and high variance. And this will overfit, this will underfit. So you would need to find something that is not very simple and very complex, but you will try to find something in between. And how we'll do that, we'll be seeing now. So to do that, we generally do something called as a learning curve. Okay. So learning curve tells you if a model is overfitting or not. So let us start with this example. Say you have this data, right? Say you have a data set like this. That you want to fit using linear regression. Right? Right? And you have, I am giving you a function that you're going to use here is, say, a cubic function, ax cube plus bx plus c. You see what happens is you will be given some as your training points and some as your test points, right? So initially, what I'll do is I will take only a few training examples, say it's this many, say 1%, 2%, and I'll try to fit it. You see, if there is only one, so y is equal to f of x. If there is only one data point, what will happen? Ax cube plus bx plus c. I can simply put ax cube plus bx plus c equal to y. So you can have infinite solutions to this problem. So you will be able to fit it easily. Up to 3 data points, you'll be able to fit this completely right. Right? So initially, when you have lower data, you will have a, so this is the green one here is the training. So your train error will be very low, 0%, 1%, 80%. So when you have 80% of the percentage of training data, and say 10% is cross validation data, unseen data, unseen CV data, right? So this will give you what is, this is an unseen data set. As you had seen before, cross validation is used to select your model. Finally, you use a test set to predict. We have seen this in the first class where we discussed K4 cross validation, where you divide your data set into 3 parts, your train set, typically around 70%, 10% will be around cross validation, where you tune hyperparameters on this, and 20% is test. So you see, as you increase the training set size, your model will find it difficult to learn. So your model may have something like this, and your error will keep on increasing. So this is an ideal fit that you have. And it will sort of converge to a training loss. This is error over here, training error. But you see, when you have only one data point, here, you will not be able to say anything about a test over here. When only one data point. So your loss will be very, very high, and it will keep on decreasing. So this is what is called as a learning curve. So over training iterations about a number of data points that you're using, if at the end when they are converging, if this is small, then it is called an ideal fit. Right? Now let us consider another case where you do have an overfitting. So in overfitting, what will happen? Can you tell me? So in overfitting, your data set will be something like this. And you're giving me the most complex data function. But in reality, say the data is something like this. And you will not do that well on the unseen data. This is your test. Right? So if you have a very, very overfitted model, what will happen? This is your train. This is your cross validation. Not test, cross validation. So what will happen? You will see that you will have a very, very low training loss, training error, compared to an unseen data, which will be higher. This is your CV loss. If I'm not using, cross validation loss, I should use green over here. So this is called overfit. Percentage of training data. So you see, when you have a large gap difference between the cross validation loss and a training loss, for example, say 70% is your cross validation accuracy and 99% is your train accuracy, then you can say the model is overfitting. Similarly, if both model is predicting also, so underfit, this is an overfit case. For an underfit case, say you are forcing your model to only fit linear functions. So to this data, if you only fit linear functions, you will only go that good. You cannot be better than that. So what you will end up doing is you will have this accuracy. So your train accuracy will also be very, very high. compared to your test accuracy. So high train accuracy or train error, not accuracy. Sorry, I'm saying accuracy. It means low train accuracy, high train error. Train error and high cross validation error. This is an underfitting case. Okay. So these are the cases how you can see if a model is a complex model, simple model, or the perfect model. Right. So now I'll be giving you some. So there is another way also to see a learning curve. Through your gradient descent epochs, you may see that the cross validation and the training loss decreases. And this is for a fixed train cross validation split and not a say 7 increasing split. So over time, what happens is the model keeps on overfitting to the data. So it keeps on minimizing the loss. But at a particular point in time, what happens is the cross validation loss, since it is becoming more tuned towards the train set, it increases. So at this point, if you stop, or this is called early stopping, you can be able to tell me that this is the best. This will prevent your overfitting. So this is the point where overfitting stops in training, right? Or overfitting begins in training, underfitting stops because your red curve, which is again your cross validation error, which is generally greater than the train error, but it can also go other way around if it is much simpler. Train error. Then what happens is you will have, why did I say that? It can be even below it. So think of a data set. I will make a contrived data set where the train set is very complex. Your train set is something like this. Right? In this case, your decision boundary will be much more difficult and you will have poor accuracy. When CV error can be lower than train error. But if you have a very, very simple test set, T here, T here, then you will be seeing that you will be getting a very, very high accuracy on the or lower loss on the cross validation set. That's it. So we have learned to understand what is cross validation error, what is the error between when to stop training, and how can we understand if a model is underfitting or overfitting. But now I'll give you some hacks to prevent your model from, and some of these are very intuitive to prevent your model from overfitting. One of them, if you want to overfit your model or have high variance, make a complex model. If you make a complex model, clearly the model will overfit as we have seen over here. A neural network can be able to do this, and therefore it will clearly overfit. Right? Clearly overfit this data because you have been able to make a high variance model. Similarly, use lower data points, have higher training time as we saw here. High training time, train time forces model to perform well on train set, right? And if you use low regularization, so if you do not give any bias to the model, it will try to maximize the variance in the data, right? As we saw in the graph. Similarly, if you make simpler models, it will underfit or it will have high bias and low variance. You give more data to the model, that then it cannot do anything but underfit the data or have ideal fit, because once you're giving more data, the model automatically have to fit, cannot overfit to the data points, right? If you have very, very many number of data, it has to give you a approximate fit to the data points. Then if you do an early stopping like we saw over here, where the cross validation error and the training error it started increasing, and you can use high regularization like L2 regularization, dropout, and so on. In dropout, this is also a regularization. It is trying to reduce the number of neurons that you have in a neural network. And if you can reduce that somehow, then that is also trying to do a regularization because you're putting a high bias, telling that I want lesser number of neurons. So now, although this is all the hand wavy explanation I gave you, telling that complex models have high variance, low bias. Simpler models have low variance, high bias. So, and then you have to find the model somewhere in between, which is optimal variance and optimal bias. But we need to understand this mathematically also. What is variance? What is variance, and what is this idea of you have one is variance, the other is bias. What is bias and what is variance, mathematically speaking? So to understand that, you can read the definitions that I've given over here, but I'll write it myself. So say you have a data set D. D is your data set which has xi and yi. And this has been sampled from some PD distribution. Some data distribution you have, it has been sampled from. So for the time being, just forget about the data distribution, but think about this. Say y is defined as fx plus some epsilon. This is how you get labels, right? Epsilon being normal and say it is sigma squared, right? What is your idea? Your idea is to train a model f x given the data set D, given data set and a training example x, right? So what can you say about this? So you can say that, say if you have a particular data set D, then this is the, do you agree this is my loss? The loss that I will have, total loss, is going to be, say I'm going to define an MSE loss is, this is the model I am using, right? This is the f hat is the model. So do you agree that the loss is going to be, right? This is going to be my loss over the data set. This is the idea, that of the loss. So one thing to note, so this is clearly MSE loss. Well, it will be 1 by summation 1 equal to 1 to n fx 1 by n fx comma di. This is over the data set that you have been sampling for a particular. This is for a 1x. 1x. We'll see why for 1x. For one particular x, you will sample epsilon multiple times and you will get y's, different y's. So this is going to be your y. This is your empirical loss that you generally get. But so therefore whole loss is defined as expected value over x comma y, expected value over epsilon or the data set, f hat x comma d. You can use d as well, minus y whole square, right? So we will be taking the internal value for the time being, and then we'll see what we have to do. So the expected value of the internal data. So this is the loss for one data point. So can we write expected value of d as, I'm just going to put the value of y. If you just put the value of y, what you will get? You will get the predictions minus your f of x, which is the actual value that your function maps onto. So just for your understanding, say your f of x is this, your model will add some noise. So your y's are not always on the line. They have some more noise. And your objective is to train a model such that it is able to fit the data, right? And not the noise, actual pattern in the data, and not the noise. So I wrote y as f of x plus epsilon, right? And then if you just expand this, what will you get? You will get expected value of f hat x comma d minus f of x whole squared, right? Plus expected value of epsilon squared plus 2 into expected value of epsilon into expected value of. Now you'll ask me, why am I writing it in this product of two expectations? I will tell you, This is because of this property that epsilon is independent of f and f tilde. This is your noise, which you do not know. So this expected value of epsilon is 0 because epsilon is distributed as normal 0 sigma squared. So you get, and you know expected value of epsilon square is nothing but the variance of epsilon, right? How do I tell you that? This is because expected value of epsilon minus expected value of epsilon whole square, which is nothing but 0. This is equal to variance of epsilon, which is equal to sigma squared. So sigma squared plus expected value over the data set f hat xd minus f of x. Right? So now the idea is, how do I categorize it into bias and variance? So I know this is noise, right? I know that this is noise. I want to categorize it as bias and variance terms, right? So what do? I end up doing is I add to this quantity the expected value over the data set. What are you going to predict? This is the average prediction, your average prediction for x, average prediction for y, right? And I'm going to subtract the same expected value from it. So generally, if it is a fixed model, this is going to be fixed for a data point. But generally what happens is I'm going to model that using the epsilon term over here. Not epsilon term, I will be modeling it in some. If it is a probabilistic model, then I will be taking x expected value. Otherwise, this is just going to be a simple sum, simple value, a simple constant, I mean. So now if I expand this, what will I get? I'll get expected value of f hat x. I'll take these two, this term and this term, minus expected value of d f hat of x comma d whole square plus expected value of over d, expected value of d over x comma d minus f of x whole squared plus 2 into expected value of fx comma d minus f hat of, or expected value of f hat of x comma d into expected value of x comma d minus fx. So see, dependent again. So this is a constant over the data set. And again, this is a constant. This does not depend on x, depend on d, because you're taking it because the expectation is over d. So now this term becomes 0. This is 2c expected value of minus expected value of f hat, which is nothing but 0. So you end up getting this closed form, expected value of f hat of x comma d minus expected value of d f hat of x comma d, right, squared plus expected value of, so this again, this is a constant, does not depend on d. Look at this interesting thing that you have. What do you have? Minus f of x whole square. So your term becomes what? Your expected value of d, expected value of x, f hat of x comma d minus y whole square becomes expected value. So this is nothing but the variance of f hat of x comma d. See, x minus expected value of x whole square is defined as the variance of x. Recall from your first few classes of probability. So this is going to be the variance of over the data set D of the predictions of your model. Plus you define this as the bias. So bias of D squared plus sigma square, where bias is defined as expected value of D minus f of x. So this is seeing, so what is this? On average, how much does the prediction vary from the actual fx? So this is how you defined as the bias. Again, you define variance plus bias square, and this is error. So you see for a fixed error, you can have bias variance increase. What happens? Error is fixed. Then you have variance plus bias squared plus sigma squared is equal to error. So if this is fixed, your bias increases, your variance have to decrease. So if you plot this graph of model complexity again, so you see, I told you this is an optimal value. Your bias or your variance keeps on decreasing. Sorry. And which one will be high bias and which one will be, as your model complexity increases, your variance keeps on increasing and your bias keeps on decreasing, because you are going to be much closer to the actual value as you go higher and higher, but your variance will increase. What you see is, therefore, this sum is the error. I hope this is a good explanation of trying to understand as you grow, make it a model more complicated. You will have lower number of bias, but higher amount of variance. So with that, we end on analyzing this model. I thought I'll have started the unsupervised learning algorithms, but today I'll not start it. Instead, just do the. I'll start with. I'll be doing the questions on implementation of the neural network, because people, I think, are having problem with joining because of the rains that are happening. So, okay. So I'll be completing today's session by seeing how to implement the neural networks, and then we'll stop. So I'll stop sharing from this. Okay. I'll share my screen. I hope you can see my screen. Now this is where I implement my neural network. I'll just keep my notes to the side so that you can have a look at it. So I'll keep this. Where is it? Yes, here it is. Let us see when it will come up. We'll be starting. So now you can see on the left, I import my data sets, my NumPy arrays, my pandas data set. So these are this is on a specific or a very special data set known as in in teaching people how to do regression, and this is a very famous data set. People in California try to predict the house prices, and the data set is pretty clean. So I import these data sets, I load the data. So you what data sets do they have? So they have medical insurance, house age, number of rooms, number of bedrooms, population in the area, latitude and longitude. And there are some 8 features that this housing data set has. And then if it has some thousands of data sets, so just a moment, I just want to load this. Just to, yeah, now I can see. So you see, I have this. I don't have it yet. Yes, now I have it now. So the backpropagation is here. I'll just show it when it's required. So I have this data. As I told you, we need to normalize the features. So what I'm doing, I'm taking the mean of the features along the feature axis, subtracting the mean and dividing by the variance. So that's the normal distribution I'm doing. And you see, once I do that, I get the mean of the features to be 0 and standard deviations to be 1. You see the range of y is between some 1.14 million to 5 point some million rupees. So I'm not going to do anything to the y, just scale the x. So now you see the MLP. The MLP, I've written a class which will take the x trained dataset, the y trained dataset, and the architecture details that you'll get. So, and here what I'll do is I will initialize the weights, as I said, randomly, because I don't want them to learn the same values. I'm initializing them for each of the layer. So you can see for 1 to number of layers. And then I define some ReLU functions, which is maximum of 0, v, as we had seen. Derivative of a ReLU, which is the maximum of 0 and v or 1, because we have seen that we either want 1 or 0 in the ReLU function. So just d-ReLU, absolute value of this, so maximum of this. So whenever you will get a lower value, you will be taking this value to be 0. That's the idea. So whenever v is negative, this term v by absolute value of v is going to be positive, going to be negative. So you'll get 0. What was the derivative last time we have seen for ReLU function? Then MSE, so finally, in the last layer, I define an MSE cost function, which is for predicting the actual predicted cost versus the actual cost. And I took the derivative as I had shown in this example where the loss was calculated as z minus y. The forward propagation, as we defined, v is wz l minus 1 plus b, wz l minus 1 plus b, as we had defined before. You can see here. Similarly, so you can see this equation I've implemented over here. Z is the output, the ReLU function. I'm using only ReLU functions over here as f to the forward propagation. Now in backpropagation algorithm, what I do, I just implement these steps. So you see, I do this dynamic programming approach where here it is. So I will take the local gradient. The local gradient is defined. So you can see the local gradient is, so if it is the last layer, I calculate the MSE loss, the derivative, or I calculate the local gradient. The local gradient is defined as the gradient at that layer into the derivative of the ReLU that we have seen here. So this square bracket that we have defined over here is the local gradient. And then with that, I take the dot product with your outputs of Z transpose and divide by the number of training examples. Similarly for B, as I told, we'll sum over all the training examples that I have done over here, over all the local gradient functions. Finally, dz is nothing but W transpose the local gradient. So this is how we define the gradient for all of the steps backwards. And then I will do a batch. I will select k examples from these 20,000 training examples, and I'll train the model. So you see, I'm training the model. After every epoch, the loss is decreasing. And we see a lower data and we see a good MSE. So around 1 million is the error that you're getting, which could have been around 5 million if you're just taking randomly. So here, I'm doing it with something called as a inbuilt library, which is TensorFlow. Here in TensorFlow, I'm going to use a dense layer and I'm going to select the same activation function. So architecture details. So in the architecture details, just to show you, I have using 8-layer neural network followed by 8 layer as the input, 32 layer as the intermediate feature, 16 as another layer, and 1 as the output layer. The same features I'm going to use over here. And you see 8, 32, 16, 1. And you see the outputs over here. So for using Keras and using my model, both of them have same accuracy. So with that, I stop today's session. So if you have any questions regarding the implementation, please stop me. Or what I'll do is I'll stop sharing my screen. I'll wait for a minute. Any questions? Okay. So today we'll begin with next day. What I'll do is I'll begin with unsupervised learning. We'll do k-means, k-medoids, and cluster learning, and the last part we'll do PCA and LDMs in 22, 23, and we'll try to finish it off in session 24 by doing k-mean GMMs. So if we don't get time for GMMs, we'll leave it out because it's not there in the syllabus. But at least the k-means, k-medoids, hierarchical clustering, and the last one is the what you're going to do is LDMs and PCA is what we'll have to do at the end. So with that, I'll stop today's session. And let me know if you have any questions. I'll be available in the Teams group. And see you on Tuesday.